Anytime we have an unknown compound, often the easiest way to determine its formula is to oxidize it or light it on fire. By doing so, it will go through combustion and produce water, carbon dioxide, and other gases, often oxygen, but they can be others. By doing this, if we've determined the amount of water and carbon dioxide and gas produced, we can then determine the empirical formula, or the simplest ratio of one element to another in that compound. If we know through spectral analysis the molar mass of the entire compound, we can divide the empirical mass, so the molar mass of the empirical formula, by the molar mass, which will give us of the actual compound, which will give us a relative, or should give us a whole number, that we can multiply the entire empirical formula by to determine its molecular formula. Now, some compounds only have empirical formulas. These are typically ionic compounds. In ionic compounds, the formula unit is what we see as the formula. Because ionic compounds don't form as one sodium to one chlorine, the ions bunch together in crystalline structures, the formula unit, or empirical formula, is simply the simplest ratio of one to another. So we will never have a molecular formula for an ionic compound. The only exception is if we have what's called a hydrate. In a hydrate, water is tacked into, or is held inside of, the crystals of an ionic compound. We often refer to these as dot waters. If I remove the water from, say, sodium thiosulfate pentahydrate, which is what this would be called, I have sodium thiosulfate anhydrous, meaning it has no water in it. Your first lab, well, technically your second lab, deals with removing the water from a hydrate and producing an anhydrous compound. Some compounds do have both a molecular and empirical formula. Here is the here is the empirical formula for this compound. The molecular formula is the actual ratio of one element to another. The ratio is the same, but simplified in the empirical formula. Let's do a problem like you would be asked to do on the AP exam, using empirical and molecular formulas. So here we read, a compound is composed of carbon, nitrogen, and hydrogen. When 0.1156 grams of this compound reacts with oxygen, meaning it's combusted or it's oxidized, 0.1638 grams of carbon dioxide and 0.1676 grams of water are collected. What is the empirical formula? Again, I start by highlighting, or at least underlining, what exactly I'm being given and what I'm being asked to find. I'm given these values, one of which is the compound in question, and two of which are carbon dioxide and water, so what this compound has decomposed into. I'm being asked to find the empirical formula of the compound. So the easiest way to do this would be to write it down. Let's write an equation that uses all of this information. So here's the equation as it was given to us. A compound plus oxygen gave us carbon dioxide, water, and nitrogen as its byproducts. And then if we add in the values that we were given for each of these compounds, we were given 0.1156 grams of the compound, underwent oxidation to produce 0.16538 grams of carbon dioxide and 0.1676 grams of water. Now, nitrogen out here was produced, but we don't know how much. So we're going to have to come back and fill in that blank eventually. Now, when in doubt, always, always, always go to moles. So we can't do that with the compound because there's no formula here. But we can with carbon dioxide. So let's go from grams of carbon dioxide to moles of carbon dioxide. Grams below, and every 1 mole of carbon dioxide, how many grams are there? That's 44. 12 from carbon, 2 times 16 from oxygen. That's where we get the 44 from. So we find that we have 0.0037 moles of carbon dioxide. Well, we can look at that and say, okay, in carbon dioxide there's 1 oxygen. So we would have the same number of moles, there's 1 carbon. So we'd have the same number of moles of carbon. So therefore we have 0.003723 moles of carbon produced from this oxidation. Let's do the same now. The next element that's in this compound is hydrogen. Let's look at hydrogen and add hydrogen into the mix. Again, we're given water. It's the only place the hydrogens could have gone. So let's do the same calculation, but now we're going to solve for the moles of water. We were given 0.1676 grams of water, and we're going to figure out how many moles of water we had. Grams go below. In 1 mole of water, how many grams of water are there? There's 18. 2 times 1.01 from hydrogen plus 1 times 16 from the oxygen. Comes out to 18. When you divide this out, you end up with 0.09311 moles of water. Now we can't just go straight from that and say therefore we have 0.09311 moles of hydrogen, because we don't have just 1 hydrogen here, we have 2. It's like an organ bank. You cut up a person, you have 1 heart and 2 lungs. Well, you've got 1 carbon in this, you've got 2 hydrogens in this water. So we've got to look and say, okay, we won't have just 1 of these, we'll have 2. So we're going to take this and multiply it by 2 to account for the 2 hydrogens in water. So we determine that we have 0.18622 moles of hydrogen. Now we can look at this nitrogen and look at how much nitrogen we are actually were produced. We need to figure out how much of this mass of this compound was contributed by these carbons and hydrogens. These carbons and hydrogens could only have come from this compound. The only other reactant here is oxygen. So the only place that carbon and hydrogen could have come from is this compound. And it's the same place the nitrogen came from. So if we convert these back to grams and subtract them from the mass of the compound, we'll determine how many grams of nitrogen that were present, and then we can figure out how many moles of nitrogen we had. So we set up our conversion from moles of carbon back to grams of carbon, and moles of hydrogen back to grams of hydrogen. And when you multiply these out, you end up getting 0.04471 grams of carbon and 0.01881 grams of hydrogen. Now together with nitrogen, they're going to equal the mass of the compound. So that's simply algebra. Are you smarter than a 5th grader? This plus that plus n equals that. Solve for n. And we find that nitrogen had a mass of 0.05208 grams. Again, we never do anything with grams, so we're going to convert our grams of nitrogen into moles of nitrogen by dividing by the molar mass of nitrogen, which is 14. And we find that this compound contains 0.003717 moles of nitrogen. Now we're going to take our moles of each element and we're going to set it up in a table. So in our table, we typically always start with carbon. Since carbon can have up to 4 bonds to it, it's almost always our central element, which means it almost always comes first in a formula. So our formula is going to, and it's almost always followed by H. So our formula is probably going to be CH and N, and we're going to look for these values, how many of each we'd have. So first let's transpose, let's take down our moles of each element. So here we have our moles of each element. If we divide by the smallest of the three, we'll simplify it, hopefully into a whole number ratio. If we don't simplify it into a whole number ratio, we simply divide, well, we'll cross that bridge when we get there. So when we divide by the smallest mole, which in this case happen to be nitrogen, when we divide everything by 0.003717, for carbon we get approximately 1. 1.0016, that's approximately 1. Same with hydrogen. When we divide 0.018622 divided by 0.03717, it comes out to be approximately 5. So this is a nice whole number ratio here. We can just drop those right into our empirical formula. So what I would write for my AP grader, make it nice and easy so I get some points here, I would say 1 to 5 to 1 ratio. Therefore, the empirical formula equals C1H5N1. I realize I'm slightly off the screen. Now, part B says the molar mass of the compound. So the actual molar mass of the compound is 31.06 grams per mole. What is the molecular formula? So again, highlight what we're given. We're given 31.01 grams per mole. So remember that the molecular formula is equal to the empirical formula to some integer, where this integer is going to be the molecular formula's molar mass divided by the empirical formula's molar mass, or the empirical mass. So what is the empirical mass of this formula? Which, if we total up the number of carbons, we have 1 carbon, so that's 12.01. We have 5 hydrogens, so 5 times 1.01 is 5.01. And we have 1 nitrogen, and nitrogen is 14.01. So if we add up all of those, we end up getting 31.07, which is rather close to the molecular formula. If we divide one by another, we find that N is 1. When we divide one by the other, we come out with 0.99, which is really close to 1. So we're going to say, therefore, that N is 1, and therefore our molecular formula is the same as the empirical formula.